Hello and welcome to Camworks Video 1, Basic Machinable Features. In this video we'll be covering in a little bit more in depth part perimeters, face features. So to start with, what we need to do is we need to open the face demo. It can be found on the M drive and it should look something like this. Pretty boring looking block. Just looking at it, we can see, from the sketch, it's a 3x4 block, and it's been extruded 1.57 inches. So kind of an arbitrary block. And what we're going to do is we're going to learn how to use Camworks to generate machine code that could create this. So the first thing we'll do is we'll go to Tools, Add-ins, and we will add in Camworks. Once Camworks is added in, we can start our process. So going back to the design cycle with Camworks, we've already got the part modeled. So we've added in Camworks, so we can change to the Camworks feature tree. We can define the machine, and we can define the machine. So going back, going to the Camworks feature tree, we define the machine. Well, we want to be working with mill inch, so we click select, and we want to be working with crib 4 English for the tool crib. The rest of it doesn't particularly matter because we're not actually going to machine this part, and so therefore we're not working on a real machine, just the demo machine. The next up in our thing is to define the stock. So we'll go back, double click on the stock. Right now it's set to, oh well, look at that. The bounding box stock is exactly what our part is. If we had stock like this, we wouldn't need to do any machining. But stock that comes in 1.57 inches it's a relatively specific stock size. So let's pretend that we got in the y-axis it was a little bit bigger, and maybe we could say it's 0.18 too big. And what that'll do is that means our stock would be 1 3/4, which is probably a little bit more reasonable. So next up in our list is we define machinable features and generate an operation plan. So what we'll do is we'll go back and just like we did before, we'll check what Camworks extracts as our machinable feature. And we can see that when Camworks didn't extract anything, it looked at it and didn't do it. And the reason for this is because Camworks not set up to recognize face features. So this is an important lesson to know. While many parts you can just simply extract machinable features, generate operation plans, and generate toolpaths, and it will get you very close to a end result, sometimes you have to do things manually. So in this video I'm going to show you how. The first thing we have to do is we have to set up a mill part setup. In order to do this, what this is this is basically the orientation of the part in a standard milling machine that we're going to use to cut it out. What we can imagine is we would just put it in as we see it now, and we would be able to machine this top surface, machine all this excess stock off. So we're going to right click on Stock Manager, put in a new mill part setup, and we're going to select this top plane, and we can see that our origin is all the way up here in the top left corner. This is fine with me, so we're going to hit OK, and now we have a mill part setup. What this is going to allow us to do is if we right click on this, we can insert a new 2.5 axis feature. So we're going to click a new 2.5 axis feature, and we can see that there's a bunch of different types. Some of these we're going to go a little bit later in the video, and some of these will be covered in subsequent videos. For now, what we're going to do is we're going to do a face feature. And what we have to do is we have to select entities. Now these entities can be sketches, these entities can be faces, these entities can be lines and contours. It really depends on what type of feature you're doing. Right now we're defining a face feature, so we need to select a face. And we're just going to select this top face. Now we can click Next, and now we can see, and it's somewhat difficult because the stock is teal, but we can see that this has highlighted all of this extra stock, and what that means is this is the machinable feature. This is essentially what Camworks is interpreting that we want to get rid of, and this is exactly what we want. We can have a couple of different strategies. What the strategy is going to do is we are defining a machinable feature, but we're not defining specific operations in order to cut out this machinable feature. The strategy will determine how Camworks will select operations from these features automatically. It's always possible to manually define an operation, but generally, when you have a particular feature, going at it a certain strategy is always the way to go, and that saves you the trouble of having to manually insert all these operations. To give you a little bit of explanation, there's three options for this particular face feature. There's coarse, fine, and shell. So an example of the different operations that could be done is a coarse operation may tend to choose a larger and more aggressive cutting tool, whereas a finer operation would use possibly only a finishing tool. A shell will use a shell mill, which is a specialized type of tool. And then we can also do things like offsetting the profile, where it may overhang the edge of the part in order to, for various machining reasons, to perhaps get rid of a burr or whatnot. And we can use or we could also use the stock extents to completely bound where we're cutting. There are various reasons for doing any of these, and you're going to have to get comfortable experimenting around. If you see something you're not sure, you try it and see what it is. A lot of these options are here for machinists who may want to do something special. For now, we're just going to leave it at coarse, and we'll leave it at use stock extents, and we'll see where that goes. So now we can either hit finish, or we can hit next and see if there's any additional features. For instance, islands. We can imagine if there was a boss somewhere on this, we could add islands where it would not cut. For us, we don't have this, so we're just going to hit finish. And now you can see that it's already asking us for another additional feature. We can test this because we can see we've added our face feature 1, and this is allowing us to add more additional features. We don't want to for this part, so we're going to hit close. And now we have a nice feature to work off of. Now what we can do, now that we have some features, we can see that Generate Operation Plan has come up. So we're going to click Generate Operation Plan, and we see that it generated this face milling operation. And it seems okay. It uses a face inch, looks like a 2-inch face mill. Seems reasonable to me, so we'll generate the toolpath and see what it goes. So again, going back to our design plan, we've defined a machinable features. In this case, it was using manual feature recognition. We've generated an operation plan. We have not adjusted operation plan, but we've generated toolpaths. Next, we're going to simulate the toolpaths and determine whether or not they're reasonable. So going back, we're going to generate toolpaths, and we can see that what this is doing is this is simply cutting across and then cutting across again. So simulating and slowing it down a little bit, we can see that it's cutting, and we can see how much the part may overhang. I could just pause this and see that there's a small amount of overhang. Continue. Sometimes when it's playing, SOLIDWORKS can be a little bit buggy. And it seems to be working just fine. So with that, we can show compare. The part looks all green. It seems to be working just fine. But you never know. Maybe we don't actually have that tool. Maybe we're cutting too aggressively. So what I'm going to do right now is I'm going to open up and edit the definition of this face mill and walk you through a little bit about what all of these tabs mean. So we've already seen the tool tab where it lists the tools, and we can go into the tool crib and select different tools or different tool holders. I think for this application, and you can sort of see where your mouse is, that's the tool we have selected. This for facing seems like a reasonable cutting tool. So I don't think for this tab we don't really have to do anything. Next is F/S. This stands for feeds and speeds. Right now this is defined by a library, and we are cutting at 439 service feet per minute at a spindle speed of 838 with a 0.01 inch feed per tooth at 24 inches a minute with a Z down of 5 inches a minute and a lead-in feed rate of 5 inches a minute. Now, a lot of these are going to be somewhat foreign to you, but hopefully a lot of them are somewhat self-explanatory. For instance, Z feed rate has to do with how quickly the tool moves down or up in the Z axis, and XY correspondingly in the X and Y axis. A lead-in feed rate, you can imagine, there's some situations where you may have the part lead into the cutting toolpath. This lead-in feed rate would be how fast it's moving during that lead-in. Spindle speed should be self-explanatory. Service feet per minute is a somewhat involved calculation, as it has to do with the type of tool you're using, how many teeth the tool has, and how fast that tool is spinning, and how fast the tool is moving. Ultimately, these calculations there's many calculators, there's an internal library, and but what I find is best it is always best to find somebody who is running the machine shop and verify with them that you are cutting at appropriate speeds by simply asking them what is an appropriate spindle speed and feed rate for any given cutting application. So for us, we are cutting about 0.18 inches of, looks like steel, and we're cutting at about 24 inches a minute with a spindle speed of 838 RPMs. To me, this is a very aggressive cut. Depending on how you're holding down the part, it may or may not be able to take it. Also, depending on what your tool can take, it may or may not be able to take it. So again, whenever you're cutting something out, you should always consult a machinist before you actually run any of these numbers. To change any of them, you can simply go to define it by the operation, and you can manually control any of these numbers. Moving to the next tab, we have the facing tab. This concerns things, for instance, maximum step over. Right now we are allowing the part to cut, and then just sort of like you're mowing your lawn, you're not going to go right at the edge. You want to do a little bit of an overhang. That way you make sure you cut all the grass. How much you step over is defined by max step over. And then there's also minimum sides offsets, which is how close do you want to get to the sides, and depth parameters. For instance, cutting 0.1 inches with a face tool, that's a pretty aggressive cut. We're cutting almost 0.2 inches. So depending on our face tool, we may want to decrease this. So I'm going to decrease this down to 0.1. Also the milling type, climb or conventional. Ask your machining instructors. Hopefully they have already educated you on the difference between climb and conventional. In one, the part has a tendency to pull itself into the tooth of the tool. In the other, the part resists the tool and is actively being pushed away from it as you machine. Or you could do it zigzag, which is actually what we're doing here. So again, go through these, look at these, see what makes sense, see what doesn't. What doesn't make sense, ask your instructor or your machining instructor. But what we've changed is we've changed the cut amounts to be a little bit less aggressive. Next is NC. This is defining rapid planes, clearance planes, and feed planes. So you can imagine, for instance, in a very 3D part, sort of like the one shown here, after you cut, say down here, you might come up relative to where you cut, but if you start coming over to this way, and you wrap it over this way, you're going to hit this island top. So this rapid plane is basically a plane that you set up that's over your part with respect to the 0, which is defined right here, and that was defined when we selected our mill part setup. And based off of that 0, so right now we can see that 1 inch over our 0 plane, so that'd be up here, is our rapid plane. In other words, the machine will never rapid below that plane. This is a useful definition to avoid crashing the machine at high feed rates. Clearance plane is another similar feature. This is more how high you have to go up to clear whatever feature you're working on. And then there's a feed plane where in this it's the previously machined depth, but in other cases it may be a current machine depth or various things like that. And then there's some additional features which we won't get into. Next is feature options. This sort of shows the feature and shows how the machining depth is 0.18. This is from the machining feature. We can override it if we wish, but usually it's pretty good about getting the right depth. Next is leads and links. As I said before, you can lead into a cut and lead out. We don't really need to worry about leads and links for this particular cut. And then we can establish upper and lower travel limits, contain and avoid areas, which we'll get to in a different video. Posting information. This is generally just showing whether it's an absolute or and what kind of coolant. This you don't usually need to change. And then an optimize feature that will show you approximately how long the toolpath is and how long the operation is expected to take. So we're going to hit OK. Now, as you see, we made one change, and that was the max cut depth that we were giving it. And now you can see that it's going through 2 passes. So to simulate it again, we hit play. And we can see it takes 1 cut and then another cut before it finishes. And so right now this is looking pretty good. So we could, what the next step would be to do is post-process. We could simply click post-process, save it somewhere. So I'll just save it to the desktop and click play. We see it generates G&M code. We can read the G&M code right here. This is a pretty short one. It's only 30 some odd lines. And if you're familiar with G&M code, you can actually read this and know what all these mean. But if you're not, then that's fine too. You need to make sure you click play and it goes all the way down before you hit OK. And there we have it. Now this is a pretty simple part. But what if, for instance, we remember, so this is, we're going to go back to the feature manager and we're going to look at the stock. So we said 1.57 inches isn't something you're going to be able to easily find in standard stock, whereas a 3x4 you might be. One other thing that's worth considering is the quality of the finish. Now, if our stock is already 3x4, then we're stuck with the stock edges, which may or may not be scuffed, scratched. These corners may or may not be sharp. So what I'd like to do is I'd like to maybe give ourselves a little bit of space around it that way we can cut. So we're going to click and we're going to give ourselves a little bit of offset in the X direction, let's say 0.1 in each direction, and a little bit of offset in the Z direction, plus and minus. Now we've got a little bit of space around. But we need to cut around this now. To do that, I'm going to show you the next feature. Again, this is something that won't be extracted normally. Face features aren't recognized, and neither are part perimeters. That's what we're going to do next. We want a tool to go all the way around the part. So to add a part perimeter, we're going to right click, and we're going to just click Add New Part Perimeter Feature. It's not something that we'd have to go into the 2.5 axis feature because it's somewhat unique. So we're going to click New Part Perimeter, and this just goes into the strategy. We can either do a boss or an open pocket. A boss will pretty much just go around the contour of your part, whereas an open pocket will actually cut all the material and sort of step its way up from the bounding box and whatever your stock is all the way up to your part. For us, we're just going to do a boss, and we have strategies: fine, coarse, taper, slot, wrapped. These all have to do with the type of operation that Camworks will generate. We're just going to click Fine. We're going to hit OK. And we see now we have this new pink feature. Pink because it does not have an associated operation. If we go to our operation tree, we still see that our old operation is still there. And if we hit Generate Operation Plan, we can see that it's wanting to update the operations or regenerate them. Updating will update the operation list for features without any operations, or if we want to regenerate, we would delete the operation we already have and then regenerate it from the feature. But because we made that one change to that operation, we just want to update it. This is going to add this contour mill. So we're going to go through and look at the contour mill. All right, but before we do, we want to see what it sort of looks like off the bat. We're going to generate the toolpath, and we're going to simulate the toolpath. All right, so we're going to hit play. I'm going to slow it down a little bit. We can see our face tool coming in first. See, now you can see our face tool has changed a little bit because our part's wider. This means that it has to go through more than just 2 times. So we see this third sort of path. The next is we select this big tool, and we cut around, and we step down one at a time, over and over and over again. And we can see already a problem. And I'll get into that problem in just a second. So we can see these tabs. And the reason these tabs is because of the tool we chose. So we're going to go and we're going to edit the definition of this contour mill, and we're going to look carefully at this tool. We can see that it's a very, very wide tool, unrealistically wide for what we need here. And we can see the flute length is 0.55 inches. But if we go to contour, we can see that the first cut amount is 40%, and the max cut amount is 40%, or if we click this percentage sign, 0.6 inches. So we're actually cutting deeper than our flutes, which means it's not going to cut. So clearly we're using an inappropriate tool for this. So going back to the tool tab, we're going to go to Tool Crib, and we're going to select a little bit more appropriate tool. I'm thinking something like a 1/2 inch or close to that end mill. So what we're going to do is we're going to look around. We'll see. I see there's an 3/8 inch end mill. So we'll just select this and click Select. It's going to replace the holder. And we can see this is a much more realistic contouring end mill. Going to feeds and speeds, we can see them. Right now, we can see that it's 8,800 RPMs. This is very fast, faster than most machines at MCC can run, indicating that this here should be changed. But because most of you don't have the background to be able to evaluate speeds and feeds, when checking these feeds and speeds, always check with your instructor. Going to contour, we can still cut out 0.6. A good rule of thumb is 1/2 the diameter of the end mill. We're using a 3/8 inch end mill. So what I'm going to do is I'm just going to change it back to percentages and click 50%. This is going to take longer to cut because it's going to have to go down in much more steps. And I hit enter so you can actually see the regenerated toolpaths, and it's going down quite a lot. Going back to editing the definition, we can see whether we're doing a climb or conventional, and a few other things, including allowing side parameters, an allowance to not quite go all the way to spec. We can define our rapid planes. These rapid planes and clearance planes should generally be the same throughout all of your operations. And we can see we can override machining depth and do a couple other different entries or possible lead-ins or lead-outs. Right now we're just set to plunge and then go. We could do lead-in and lead-out with a small arc leading in or a small arc leading out. Going to advanced, there's nothing really here that we want to change. Posting, looking at the optimize, we can see that this is estimated to take about 2 minutes with a total of 178 inches of tool travel. So we hit OK. And now we've already generated the toolpath, but we can click generate again just in case it did not update. And now we can simulate. And now we can see that this part is done and cut out. If we compare it, it's all green. So now we could post our code. I'll just overwrite the face demo that I saved before. I'll just replace it, and I can hit play. And now we can see that we went from about 36 lines to 135. And we're cutting a lot more. So now we're good with that. We can save our part, and there it is. So this sort of shows you how to manually insert a 2.5 axis feature and goes into a little bit more detail about face features and part perimeters. In the next video, we'll be covering pockets and bosses and holes. Pockets and bosses are very similar to part perimeter in terms of the layout of the options and what the operations look like. Holes are a little bit different than what we've worked with so far.